Welcome to video 3 of chapter 4, where we will look at genetic disorders. And we will begin with single gene disorders. So these disorders can occur from inheriting a pair of recessive genes. So this is just like what I was talking about for eye color. These specific disorders are just dependent on one single pair of genes, just like your eye color is. So you get one gene from your father, one from your mother. If you get a recessive gene with the disorder from each parent, then you would show your phenotype would show the disorder. You would develop it. The parents may not even be aware that they carry these recessive genes. It can also happen through mutations, where each member of a pair of genes undergoes some kind of mutation that cause the disorder, or you can inherit mutations from each parent that lead to the disorder. But those are more rare cases. The typical case is that your parents carry a recessive gene for a single gene disorder, and you get one from each parent. Once again, this would affect, just like eye color, when I was talking about blue eyes, I said that 25% of the children would have blue eyes. Similarly, if each of your parents carries a recessive gene, you would expect 1 out of every 4 children to show the disorder. Some examples are listed here. We've got Tay-Sachs disease, which is a real horrible disease. It's a progressive neurological deterioration that goes on and causes the death to an infant, usually by the age of 5. It's no one lives very long with Tay-Sachs. PKU is a disorder where the child is missing an enzyme that normally would break up certain proteins in the diet, because they're missing this enzyme and these proteins don't get broken up. They end up causing intellectual disability, usually by the age of 1. They now routinely test for PKU right after birth. They take a blood sample. It's one of the things, like, if you've given birth or been around a new birth, they'll come in and take a blood sample, usually the first day, from the baby. And one of the things they test for is PKU, because if the child has PKU, they can actually prevent further damage by going on a specialized diet, which they will have to stay on for the rest of their lives. They have to avoid certain foods that have protein that they can't break down. So if they actually stick to the specialized diet, they can grow up fairly normally otherwise, but there will be a number of things that they cannot ingest. What else we have here? Sickle cell anemia. That's where your blood cells are sickle shaped instead of oval. A sickle is like a crescent moon. Think of it as a crescent moon. So it's a little it's got kind of like more pointy edges. It's not nice and oval, and so it can clot because you've got these crescent moon shaped blood cells. They can kind of hook on each other and then clot up in various places, causing severe pain or damage in various parts of the body. It affects African Americans much more than non-Latino Caucasians. Cystic fibrosis is where the body produces a thick, sticky mucus that clogs the lungs and makes the child vulnerable to various pulmonary infections. Anyway, these are examples of single gene disorders, just reliant on one single pair of genes. There's also another example that I don't have on the slides here, and it's a special case called X-linked inheritance. Now, remember when when we looked at the figure, I'm just going to go back real quick. We looked at the figure of the genes here, and I told you to note that final pair, the XY sex chromosomes here, and how much smaller the Y is than the X. Well, this is what can lead to what's called X-linked inheritance. Let me get back to where we were, and I'm going to go to my whiteboard, and I drew a little picture to help explain it. So ignore what's on the right side for now. We're going to cover that in the next video. But so just looking at this picture here, this is looking at the 23rd pair, the sex chromosomes. On the left, we have a pair of X's, so we know this is a female. And suppose the mother has a recessive mutated gene. Let's say she carries, for instance, the recessive hemophilia gene, which is carried in this 23rd pair. Another example would be red-green color blindness is carried in this 23rd pair. Anyways, hemophilia, before I go on, that's when your blood doesn't clot normally, just in case you weren't aware. Anyway, so let's say the mother has a recessive mutated gene. So the mother's chromosomes on the left, and she has a girl. Well, the father most likely passes a normal gene, because normal genes are much more prevalent. I mean, it's rare enough that it's rare to have a hemophilia recessive gene, for instance. And so it's kind of like a backup plan for you have a little girl. Well, the father's dominant normal gene just overrides that recessive gene. And so the girl grows up normally. However, the male, remember, the male has that little Y chromosome. And the little Y chromosome carries far less genes than that big X chromosome. So you can see there's nothing to match up with that recessive mutated hemophilia gene that the mother's carrying. She sends the X chromosome, the father's sperm has a Y chromosome, and so the male develops hemophilia or red-green color blindness. There's a couple of other X-linked inheritance things as well. Something to do with baldness is carried on here. I mean, there's a few different traits that are passed this way. And so if it's not obvious yet, these are things that affect males significantly more than females. Most females are protected because the father sends a dominant normal gene to the female, and it overrides the recessive gene that the mother may have. And so in order for a female to get hemophilia or red-green color blindness, both the mother and father would have to pass, these rare recessive mutated genes. But for males, it only takes the mother having to have the condition and pass the recessive gene. Once again, the mother may be completely unaware that she carries a hemophilia gene or a red-green color blindness gene because she would not be showing those symptoms. She would, in most cases, have a dominant normal gene that her mutated recessive gene is paired up with. So X-linked inheritance affects males far more than females because of this small Y chromosome in the 23rd pair that is missing certain genes that can override, recessive genes passed on the mother's X chromosome. Okay. Let me go back to the PowerPoint. Where is it? Here it is. Okay, so those are single gene disorders. X-linked inheritance is a special case occurring only on that 23rd pair, and it mainly affects males. That's cool. Then we have chromosome disorders. So these are disorders that involve chromosomes rather than genes, which are the little parts of a chromosome. These involve like whole chromosomes that are missing, or there's an extra chromosome, or there's a damaged chromosome. So it may be the addition, the loss, or the breakage of parts of chromosomes. The primary example, and the most frequently occurring example of a chromosome disorder, is Down syndrome. Let me go to the next slide. This by far is the most prevalent of chromosomal abnormalities. It's when the offspring has an extra 21st chromosome. So something went wrong in the machinery when the father was producing his sperm or the mother producing her eggs, and they, instead of passing one chromosome, they passed two chromosomes from this 21st pair, and somehow the child ends up with three chromosomes instead of two, and this is what causes Down syndrome. So it's a whole chromosome, not just an individual single gene. In case you don't know, Down syndrome involves intellectual disability, specific facial features, poor muscle tone, and possible problems with heart, digestion, and hearing. A couple of other examples of chromosomal abnormalities involve, once again, going back to that 23rd pair of the sex chromosomes. Klinefelter is when a male has an extra X chromosome. So instead of just XY, he has XXY, and it can lead to infertility, small genitals, enlarged breasts. A couple of the reduced armpit and pubic hair. A couple of these symptoms make sense because we consider the X chromosome the female chromosome, the Y is the male chromosome. So he has like kind of extra female characteristics which lead to his genitals being smaller, his breasts being enlarged, less hair, and so Turner syndrome is another one. This is where a female has a single X chromosome. Instead of XX, they are missing one of the X chromosomes. And you can see the description here. Certain of these disorders that affect the sex chromosomes, some of them aren't often discovered until puberty, and that's kind of where they really kind of show themselves. The person doesn't develop normally for their gender, when they reach puberty. Sometimes all throughout childhood, there may be no symptoms showing up until they reach puberty. There's some other ones as well. There's an XYY disorder where a male has an extra Y chromosome, for instance, but these are the ones I want you to know for the test. Okay. Going on here, and I will tell you that often I have a question about one of these chromosomal abnormalities on the test, so make sure you are aware of them. Then we had single gene disorders involving one pair of genes. We had chromosome disorders involving like a single missing or extra chromosome, or sometimes it's a damaged chromosome that doesn't work. We also have multifactorial inheritance disorders. So these are more complex. They result from the interaction of many genes that also interact with environmental influences. So a couple of examples are depression or autism spectrum disorder. You could add alcoholism to this list. You could add schizophrenia to this list. And let me just deal with those last two that I just mentioned. So make sure you make a note of them. Alcoholism or schizophrenia. I mean, no one is born an alcoholic, right? I mean, like, you may be born with a propensity towards alcoholism, or what's called a disposition, meaning that you're much more susceptible to become alcoholic. But as it says here, they interact with environmental influences. Somebody born susceptible to becoming an alcoholic, if they have the right environmental influences and they're never steered towards alcohol, maybe they grew up with a family that doesn't promote drinking, and they grew up, like, not desiring alcohol. I mean, if given the right conditions, they will never develop their alcoholism. So the environment has to interact with those genes. Like I said, you're not born an alcoholic. No one's born a schizophrenic either. My sister has schizophrenia and has had it since her early 20s, or maybe even earlier. But So it's been, for the last 30 years or so. And I certainly have genes in common with hers. And I know that because there are, under certain influences, I can show similar symptoms to her schizophrenia. I'll just mention, like, for instance, I went through one weekend where it seemed like my genes got triggered, and I had paranoid delusions throughout a whole weekend once. Um, it was crazy. I mean, like, I saw things in the clouds I'd never seen before. When I heard the radio, they were always talking to me. I went to a restaurant with my buddies, and I couldn't stand it because this family sitting at another table, they kept talking about me throughout the whole meal. Every bite I took, they were making comments. And do I believe that now that's true? No. But at the time, it was so real. And I ended up having to leave, and I went out to the car to get a shirt because it was hot. I was wearing a sleeveless shirt, and I had started, this was in my 40s where I started to put some weight on, and I was very conscious that they were watching and make comments about my fatness and my eating. And so I ended up going out to get a shirt to put over top because I couldn't stand it. But these voices were in my head. They were just having a normal conversation, I'm sure. I didn't want, I wasn't going to admit this, but I actually thought for a while during this weekend, for much of the weekend, that I was actually dead and I would never see my family again. And anyways, I just thought I was like going through like some kind of middle ground where, like, I was going to be taken, at any point during the weekend. And I expected that I would never make it home to see my family. I was on a weekend with some friends in another state. But anyways, it was crazy, the things that happened. And I had a little touch of what my sister must go through on a daily basis. And it was horrifying because it was so real. And even for a long time afterwards, it still seemed real. Even when my symptoms started to, to go downwards, I mean, it never, the realness of it never leaves. And so anyways, I know this is more than you bargained for, but what I wanted to point out was that we have similar genes, but my sister got triggered. And we know that there's certain stressors in life that can mix with schizophrenic genes to cause the disorder to come on. And I experienced a touch of it because I experienced certain environmental influences that activated my genes for that weekend. And my sister, though she experienced certain stressors throughout adolescence that led to full-blown schizophrenia. And so, like I said, no one's born schizophrenic, no one's born an alcoholic, no one's born depressed, right? These are, you get a lot of genes that make it more or less likely you'll get these things, and then the environment mixes in. Autism is a little different. I'm not going to really go there about how the environment might interact with the genes. So that's multifactorial inheritance disorder. It's a very complex mixture of genes and environmental influences. So given that we know that there are, all these genetic type disorders and chromosomal abnormalities, and I mean, like, should we get genetically tested? Well, the average couple has about a 3% chance of having a child with a genetically based disorder. That's not a huge risk. I mean, 97% chance of having a perfectly normal, healthy, genetically normal baby. I mean, like, it's not bad odds. But this is kind of a list of who should get genetic counseling, and some of these points listed here would increase that 3%. And if you have, more than one, characteristic that might increase it. So like things like having a family history of genetic disorders certainly will increase your odds of giving birth to a baby with a genetic-based disorder. If you already have a child, as it says here, with intellectual disability or an inherited disorder, certainly if you have one, it's more likely you'll have another, then the next one could also have a disorder. Age is a huge factor, as it says here, above 35. You should probably get some kind of genetic counseling. If the odds, just increase a little bit after 35, but once you get up into your 40s, they increase, pretty dramatically. And women giving birth in their 50s, it's almost like a coin flip. I mean, like, whether they have a healthy or a disordered baby. I mean, like, so the odds really, like, it kind of snowballs the older you get past over 35. I mean, so there's different factors that lead to increased risk. What else here? Any other ones on? If a woman has ever had a baby who died in infancy or has had 3 or more miscarriages, that's a sign that she may have some disordered genetics. So being first cousins or blood relatives, yeah, that's not good for genetics. Okay. Anyways, so it's not standard procedure to get genetic counseling, but it is available for people that want it. And there's certain things that they can test for when you go in for genetic counseling. First of all, they're going to get a family history of genetic disorders from you. They will like ask all sorts of questions about your ancestors and relatives to help determine your risk. There are blood tests before pregnancy that can determine if you have certain genes. For instance, blood tests of the two partners can determine, for instance, if you carry the Tay-Sachs recessive gene. Remember, that's a horrible disorder where the infant dies by the age of 5. They can also detect sickle cell anemia in blood tests. So if there's risks, then you and your partner can go in and test for some of these possible disorders and find out if you each have the recessive gene. If only one of you has it, you know that you're safe. Unless it's an X-linked inheritance type of disorder. Tay-Sachs or sickle cell anemia are not those. Okay, anyways, so for those disorders, both partners would have to carry the recessive gene. If you find out that that's the case, then then you would have to make some decisions about whether or not to take the risk, and knowing that there's about a 25% chance of your child having that disorder. During pregnancy, various tests can be done to look at the genetics of the developing embryo or fetus, or the developing fetus. When these tests are done, it would be in the fetal stage. Blood tests are that are given, where they just take the mother's blood in a test called the alpha theta protein test. It's basically a screening tool. It does not give you a definite answer of genetic disorders, but it tells you whether or not further testing should be done. Like, they can see if there's any indicators that you might be at higher risk. And then if there are, they would probably move on to one of these last 2 tests here. Amniocentesis. This is when they stick, a huge needle through the abdomen, right through the belly, down into the amniotic sac, and they remove a little bit of the amniotic fluid, which carries genetic markers of the developing fetus. That's typically done between 15 to 17 weeks, which is right around the 4-month mark. Now, if you want to test earlier, you could do the chorionic villus sampling. This is where they go in through they go through the vagina and into the with an instrument right into the womb, and they snip a little part of the outer layer of the embryonic sac. There's like little hair-like protrusions on the outer layer of the embryonic sac, and they kind of snip one of these, and it contains genetic material that they can analyze. It's a little bit riskier, but it can be done earlier. So it's typically done in around the 10 to 12 week mark. So that's like a whole month earlier. So that's just at the end of the 3 months compared to having to wait till 4 months. So it's a little bit riskier, but you get faster results. If you think there's a high risk, you might want earlier information. There's also one more you can add to this list. It's called peripheral umbilical blood sampling, or PUBS, P-U-B-S, PUBS, peripheral umbilical blood sampling. And this is done in either during the second or third trimester. It can be done, and they actually go in and they take red blood cells right from the umbilical cord. So that's why it's called peripheral umbilical blood sampling. They're sampling blood from the umbilical cord. If they need more definitive evidence of something, they may do that. Okay, and finally, in this section, well, what if we know that there's genetic disorders? Do we have ways to treat them? Well, unfortunately, not right now. We're working towards that. I mean, especially, it just seems like, we've identified, single genes that cause things like Tay-Sachs or sickle cell anemia, and like if we could just replace those genes, and this is what gene therapy is hoping to do, treating genetic disorders through implanting or disabling specific genes that cause the disorder. And right now, this is not yet available, but for humans at least, they are experimenting. They've experimented with animals. They are experimenting with some humans at this point, is what I've heard. So it still is probably a little ways off. It's not an easy science to replace or disable a gene. Okay, so it's being done on an experimental basis at this point. But that's the future. I mean, if we can harness that and learn to manipulate, to implant or disable specific genes, I mean, we would, it would do wonders for curing some of these genetic disorders before they start, and replacing them in the womb. Okay, and that will end video 3. In video 4, we'll start talking about behavioral genetics.